Thank you, Professor Nakata, for kind introduction. And also, I'd like to thank you, Professor Takashi Mori, for giving me a chance to give a talk today. So let's start. So first of all, so I want to remind you about the amazing ability of plants. So that is the plants collect a low concentration of CO2 from the atmosphere and to reduce this stable CO2 to synthesize glucose even at room temperature. And also water was used for oxidation reduction. And finally, it's perfect from the perspective of the LCA, life cycle assessment. So naturally propagate and no waste. So this is quite amazing. And also, plants fix a large amount of CO2. For example, this slide shows the goal of our laboratory. So the most biomass exists in forest ecosystem, and quite a large amount of carbon dioxide is assimilated annually. So this is 10% of atmospheric CO2. So that's why this system is very interesting for the CCS, carbon capture and storage. So biochar, wood is converted to biochar to store the land. So that reduces the carbon dioxide concentration of the atmosphere. So this amount, 10%, is correspond to the 4 to 5 times of the world energy demand. So that's why our laboratory intend to develop the technology of wood conversion technology into chemicals, fuels, and other very useful materials. So, this slide shows the biomass conversion technologies that involved 2 large groups. One is the thermochemicals, the other is biochemicals. So today is to focus on the thermochemicals. So conversion to produce heat, and the heat is also utilized for power generation. But the problem is the low efficiency. So pyrolysis have the potential to produce liquid fuels, charcoal, and chemicals. But the low product yield and low selectivity is a problem. And gasification also have the potential to provide the high efficiency electricity production by the gas engine turbine. And also petroleum chemicals can be produced. But the tar and coke problem is a great issue for commercialization. So for some chemical conversion technologies, the major challenge is how to control the reaction. So this is the very contrasted to the biochemical, as like the previous talk. So in this case, how to increase the reactivity. And also some chemical way also can contribute this increase in reactivity. So for this reason, so we have studying the molecular mechanism of wood burning, particularly the pyrolysis, because wood burning is a two-stage process. Firstly, the pyrolysis to produce the volatile charcoal, and these intermediates finally converted to produce heat. So when we started, we have studied these mechanisms for 20 years. But when we started, these molecular mechanisms tended to be treated as like the black box, so almost nothing known. So we intended to elucidate the molecular mechanism to control the reaction. So now, we have some information. So that is reviewed in some recent review. This is the review of reaction and molecular mechanism in cellulose pyrolysis in 2016. And this is the lignin pyrolysis reaction in 2017. So this is the major topics of this today's presentation, the fundamental characteristics. One is the pyrolysis products are unexpectedly unstable against heat. So I think most of the people do not know this very important characteristics. So today's talks mostly I focus on these topics. And lastly, is briefly introduce the influence of ultrastructure of cell wall. This is also quite important to control the reaction.